Higher Physics Notes, Unit 2, Section 3, Wave-Particle Duality. It's an interesting feature of light that it exhibits both wave-like properties but under certain conditions it behaves like a particle. Now, we cannot say that light is a wave technically, or light is a particle. What we have to say is this: light behaves as if it were a wave under certain conditions, e.g. diffraction, and interference. However, it behaves like a particle in other circumstances, the most notable being the photoelectric effect. And it's the photoelectric effect that we're going to begin with. Well, the photoelectric effect happens when light, or indeed another electromagnetic radiation, interacts with a metal. So here's the scenario. So we have a metal, and this is the surface of that metal. So I'm just going to kind of shade that in to show where the metal actually is. And then within that metal there will be free electrons near the surface. I'm just going to draw one of them. Metallic bonding is unusual in that, on average, one valence electron per atom is not required for metallic bonding, so it's just hanging around. And if you create an electric field, for example, that's what allows metals to conduct. Okay? So these electrons are there and they're not involved in bonding. Now, what Planck discovered was that if you send in light, and I'm going to deliberately draw the light coming in as a little packet with a beginning and an end, right? Like that. And I'm going to call that the name that's been attached to it, and that is a photon. So a photon is the name given to a discrete little packet of light energy. What Planck discovered was that that photon will be absorbed into the metal and will interact with a single electron. And because the photon carries energy E, it will give that energy to the electron. And it can give that electron energy so that it brings it to the surface of the metal itself. And the amount of energy required to do that is called phi, the work function. We'll write that down in a minute. If the photon has any energy left over, then it's entirely possible that the electron will be liberated with kinetic energy, so it will have some EK when it leaves. And this process is called photoemission. Okay. We talk about the electron being liberated or emitted from the metal surface. Now it turned out that the energy of the photon was dependent on its frequency, and that energy is given by the equation E is hf, where h is Planck's constant. It's the constant of proportionality. So that then allows us to set up the key equation in this section, and that key equation is this: the photon energy equals the work function plus the EK of the electron when it's released. So all of that photon energy turns into either the work function or the kinetic energy if there's enough left. If the photon energy is less than the work function, then it may raise the electron partially to the surface, but it won't be liberated. So in this equation then, this E is the photon energy in joules. This is called the work function. It's sometimes called the threshold energy as well. It's the minimum amount of energy to get the electron to the metal surface, just and no more. And this then is the kinetic energy of what's called the photoelectron. Just an ordinary electron, but it's called a photoelectron because it's been liberated from a metal by the photoelectric effect. Now we can unpack that equation to say that it's equal to hf, because the energy of the photon Planck found was hf, f being the frequency, equal to the work function, which is just a certain number of joules, and it's specific to each metal, the work function. So zinc has one work function, lithium has another, and so on and so forth, times a half m v squared, m being the mass of the electron. So that's the key equation. It's really the same equation unpacked that you should definitely have memorized. I'm just going to put in here, work function is specific to each metal. It will be a very small number of joules, a tiny fraction of a joule in fact. Okay. Now one important observation here, and it's very crucial that you're aware of this, is only one photon can interact with one electron. It's a one-to-one correspondence. One photon with one electron. So you cannot get two electrons working together to liberate an electron, two photons working together to liberate an electron. It can only be a one-to-one thing. So if the individual photon has insufficient energy to liberate the electron will not be liberated. Okay. So let's do a worked example of how this works. So, what is the photon energy for red light? Now, if you don't know the frequency or the wavelength of red light, you can look it up and get the frequency from V is F lambda. But I'm going to tell you that the frequency for red light is 4.2 times 10 to the 14 hertz. So the energy of the photon of that red light then would be E is hf. Now h, of course, is Planck's constant. You can look it up in the data table, but it's 6.63 times 10 to the minus 34, and we're multiplying that by 4.2 times 10 to the 14 hertz. You will see that it's important to have your calculator set on scientific notation, and I would suggest 3 significant figures, and I'll make that a 0 so that we're consistent. And when you multiply these two together, you get 2.78 times 10 to the minus 19 joules. And that's 3 significant figures. So far, so good. Now a more substantial example. The work function of cesium is 2.16 times 10 to the minus 19 joules. Find the threshold frequency F naught required for photoemission. B, if incident light of lambda 589 nanometers is shone upon the cesium what is the maximum kinetic energy of a photoelectron, and C, hence find the maximum velocity of the photoelectron. So, solution. Well, in part A, the threshold frequency F naught, this is the lowest frequency of photon that can cause photoemission. So basically, the work function phi equals hf naught, because if a photon had that frequency f naught, that is the least energetic photon that would just liberate an electron and no more. So if we work that out, then we know that the work function is 2.16 times 10 to the minus 19. So that implies that F naught is 2.16 times 10 to the minus 19 divided by Planck's constant, which you get from the data table. There we are. And when you calculate that, you should get 3.26 times 10 to the 14 hertz. So any incident photon with a frequency of 3.26 times 10 to the 14 hertz or greater will cause photoemission. If the photon has exactly 3.26 times 10 to the 14 hertz, it will liberate the electron but with zero kinetic energy. Okay, part B. Right, well, we firstly need to get the frequency. We've got the wavelength of the photon, but we need the frequency. So V is F lambda, commonly used, 3.00 times 10 to the 8 is equal to the frequency times the wavelength. Now the wavelength, what was it again? 589 nanometers. So that's times 10 to the minus 9, remember. So the frequency itself, 3 times 10 to the 8 divided by 589 times 10 to the minus, minus 9. And that gives me a frequency of this incoming radiation of 5.09 times 10 to the 14 hertz. Now in an exam question, I would not do that intermediate calculation. I would leave the expression as the fraction that you can see there, okay, so that I'm avoiding intermediate rounding. But for clarity, I'm going to do an intermediate calculation in this worked example. Right, we then set up our photoelectric effect equation. Plus EK. And we can unpack that to become HF equals HF naught plus a half. Well, we don't actually need the velocity yet, so we'll just leave it as EK. So HF is Planck's constant times the frequency I've just worked out, 5.09 times 10 to the 14, and that equals my work function 2.16. What was it again? Times 10 to the minus 19 plus the sought EK. So EK equals the left-hand expression, take away the 2.16 times 10 to the minus 19, and when you work that out, you should get 1.21 times 10 to the minus 19 joules. So So this incoming photon has energy that's a good bit bigger than the work function, as you can see, and so there's extra energy left over to become kinetic energy. Right, the final part was get the maximum velocity. Well, incidentally, that question said, what's the maximum kinetic energy of the photoelectron? This equation which we use assumes electron loses no energy on moving through the metal. Now in practice, some electrons don't lose any energy, but quite a number of them do. So there's a spread of energies going from this maximum that we've just worked out, assuming no losses, down to one that's a good bit lower. So that's why it's maximum. Consequently, in part C, we're looking for the velocity. We now know the kinetic energy, as you know. Ek is a half mv squared, where that's the mass of the electron. So 1.21 times 10 to the minus 19 equals a half times the mass of the electron. We'll get that in the data page, 9.11 times 10 to the minus 31 times v squared. So v squared, you can work out v squared actually, but don't round at that point. I would suggest you just keep that in the calculator until you get to v, and you'll get 5.15 times 10 to the 5 meters per second. Okay. So there is the final velocity. So that brings us to the end of part 1, and I've just realised that I don't think I wrote part 1 at the top, so I'm going to just put that here. Part 1, the photoelectric